Hi everybody, welcome to my 20th axial bar video. In this video I'm going to be solving this elastoplastic problem that you see here. We're going to plot a graph of P versus displacement of the point of application of the load. If you want to know something else about axial bars, feel free to check out any of my other axial bar videos. Alright, so if you've watched the previous video before this, of my introduction to elastoplastic analysis, you'll see my process here. I just want to bring that back because I just follow this very closely when I'm doing this question. So the first thing they want me to do is find the forces in all the members. Alright, now we can do that. It's just a free body diagram, right? So let's go into this. We make some cuts. Alright, right here. And we'll of course look this way. I'll get a free body diagram of that piece. There we go. P 60 degrees, and we have some normal forces, of course, in here. Let's just call this N2, this N1, this N1. Oh, sorry. Okay, now label some direction to do the sum of the forces. Alright, in this case we'll do it in the y direction. Alright, we didn't prove that N1 and N2 are equal to each other, but since the angles are the same, alright, we can just do that. The sum of the forces in the y to be 0. N2 plus 2, alright, because we have two normal forces, 2N1 times the cosine of 60 degrees equals 0. Alright, now the cosine of 60 degrees, I always still need to remember these little unit triangles, I guess you call them. So this is 60, 30, alright, this is shortest, so that's 1. This is longest, that's 2, that's root 3. So the cosine of 60 degrees is half. Alright, so plug that back in, rewrite this equation. We get N2 plus N1. Oh my, I forgot P here. Equals P. Alright, so those are our forces. Wait, we don't have the forces yet. It's statistically indeterminate. We need to take a look at the displacement. So this is our forces. And now we're going to displacement. Alright, so the best way to do displacement is to draw a before and after picture. So before, you can imagine it could look like this somewhat. And after, it's going to go into this sort of configuration. Like so. And then we can say the displacement of 2 is this bit here, alright? Because this is that central piece that's just moved down. Boom. Delta 2. Alright, and this piece here has got longer by an amount here to here. Alright, so drawing a right angle in here. Alright, let's extend this out. Delta 1. Okay, now if this was 60 degrees, we're assuming that this can be taken at 60 degrees too. Now, theoretically it's not, but since we're going to assume this displacement is quite small, we can just say that this angle is the same as that one. Alright, so now we have this little triangle here that's really useful. Color it in red so you can see it better. And this corner here is 90 degrees. Okay, so we can write the cosine of 60 degrees is equal to this piece, delta 1, by delta 2. And of course this was equal to half. So we can write delta 2 equals to 2 times delta 1. Alright, so this is our second equation. Displacement. Alright, now, force displacement. And we use the equation delta is NL over AE. Alright. Get rid of this paper here. And then we can sub in this into here, right? Because the displacement of 2 is due to the properties of 2. So N2 L2 A2 E2 is equal to 2 N1 L1 A1 E1. Alright, now going back to what this question was asking us in the information, all of them have a length L, all of them have an area A, and all of them have a Young's modulus E. Alright, that's nice and handy for us, because it allows us to just simply cross all this business off because they're all the same. Boom, boom. Oops, not that one. Boom, boom. Come back, come back. There we go. So we can say N2 is 2 times N1. That's our third equation. Now, just like before, we have one equation with N1 and N2, another equation with N1 and N2. So we solve them simultaneously, 3 into 1. And then we can say N1 is P by 3, and then N2 is 2P by 3. Right? So there we go. We've completed the first step of my process, if you will. Alright. And the next step, let's pull it up here. There we go. Calculate the stresses in all members. Alright. So we have the forces. So the stresses shouldn't be a big deal. It's just that divided by the area, right? So sigma 1 is just equal to P by 3A. Okay. And then sigma 2 is just 2P by 3A. Alright, stresses. So the one with the greatest stress will yield first. Alright, so that's going to be this guy here. It takes the greater component of it because it's like 2/3, right? Alright, so if this is going first, if this sigma 2 is sigma yield, that means at sigma yield it must also be P yield. Alright, oops. So take a second to understand why that's true, because it's kind of important that you realize that this is the case. Alright, so if there's a load P yield, at the time P yield is being applied, and also be in sigma yield. Alright, so in this case, let's solve for P yield. It's going to be 3/2 sigma yield A. Okay. Alright, now if you wanted to find the displacement of the piece at that point, alright, we can take a look at my steps here again. Alright, use the member that's going into the plastic region to find delta. Alright, so what member is going into plastic at this point? Well, it's going to be member 2, right? Because that's the one that has the greatest stress. So delta 2 then is equal to delta yield is equal to N2L over EA. Alright, now it's in its yield stress. Alright, so it's yielding at this point. So that means N2 over A, that is just the stress portion of it, that's going to be of a value sigma yield. So we can write delta yield is sigma yield L over E. Just like that. Kind of weird. Take a second to understand why that's true. If this member is in yield, that means the stress in there is going to be at sigma yield. So that means N2 over A has to be sigma yield, and it gives you this answer here. Alright, so when we plot this later, this is going to be like the first point of our graph. Okay, so now we got to find when it's in fully plastic region. So, if you recall, when in full plasticity, all members have the same internal force. Alright, so this actually makes it quite easy. So all members have the same force. That means N2 equals N1. So that means 2N2 equals P. So N is going to equal to P by 2. Alright. let's just write that in a more mathematically rigorous sense here. We can get bunched up. All right. Full plasticity, N1 equals N2. Let's let it equal N. So using the equation 1, N plus N equals P. N equals P by 2. Okay. So the stress now, all right, because using this handy bit of rules here, we found the forces in there. Now to find the stress in the members. All right, so in this case, we know that N2 is already in its displacement mode, so we're looking at N1. All right, so those are the angled pieces on the side. We're looking at those pieces now. So the stress in those is just the normal force by area, so it's P by 2A. All right, and if this goes into the yielding region, if this is sigma yield, this must be P yield by the same logic as we did before. All right, so therefore P yield, wow, okay, P plastic. All right, well, technically this bar is yielding at that point, but the whole structure is in plastic region, so we call it P plastic. Equal to 2 sigma yield A. And then we find the displacement of just this member. All right, delta 2 N2L over EA. Delta 2 is equal to sigma yield L over E. And we know that delta, well, this is 1, sorry. Delta 2, or the one we want to know the displacement of the at the point of the application of the force is 2 delta 1. So delta plastic is 2 sigma y L over E. All right, so let's plot these two things. All right, 1, 2, 3. So this here will be when the first member yields, right? So that was this member here. Oh, sorry, 1. That was the middle piece. And it's going to yield at Py is 3.5 sigma Ya. All right, and it's in its fully plastic region when P is equal to 2 sigma Ya. So you only need to increase this by half. Oops, to make it go into the fully plastic region. And then of course the corresponding deltas are sigma y L over E and 2 sigma y L over E. So this point has moved twice the distance. And of course we're plotting P here, delta here. Alright, so that's the answer for this question. Hope this helps you guys out a bit. Let's just review what we did. So the first step requires us to find the internal normal forces in each member, and then find which stress as a result of those normal forces is the greatest. Alright, so we found the internal normal forces. We needed to use force displacement because it was statistically indeterminate. We found the normal forces. We found the stresses in the two pieces, and we realized that sigma 2, although the rod that was straight up and down, had the greatest stress. We realized that went to yield first. Alright, so if this was at a point yield, then it means the P that was applied at that time was also P yield. Solved for it and found the displacement. Then we said at fully plastic, everything is the same force. So N is P by 2. The stress is, P by 2 divided by A. And then if it's at a sigma yield, that means P yield must be applied also. Right, P yield results in sigma yield. We solved, found the displacement of just that bar, and then related it back to bar 1. Alright, so important that you do that. Don't try to calculate number 1 directly, or else you'll get confused. Then we plotted it. Alright, hope this helped you guys out. Thanks so much for watching. I will see you in my next few videos where we just talk about fun applications.